students, welcome to the video lecture series on Chemical Engineering Thermodynamics 2. I am Jamin Pandya, Assistant Professor in Chemical Engineering Department of LJIET Institute of Engineering and Technology. So let's continue with the chapter number 3, which is a chemical reaction equilibria. So in this lecture, we are going to discuss about the relation of equilibrium constant to composition, or can say that equilibrium conversion, which denoted by Ky, and equilibrium constant, which denoted by K. So here we are going to relate the K and Ky. We are going to relate these both terms for the gas phase reaction and liquid phase reaction. But these both are homogeneous phase reaction. Okay. In previous lecture, we discussed about the heterogeneous phase reaction. Here we are going to discuss about the homogeneous phase reaction. And then after we are going to discuss about the various factors affect on equilibrium conversion. Okay, which is known as the Ky. So let's start with the relation of equilibrium constant to composition, or can say that equilibrium conversion Ky for the gas phase reaction. So for gas phase reaction, first let suppose our equilibrium constant that can be given by K is equal to capital Pi of Fi bar upon Fi naught whole raised to Vi. Okay. Now this Fi naught can replace by, for the standard state, it's replaced by the Fi bar is equal to Pi naught whole raised to Vi. So we can replace this Fi naught with Pi naught at standard state. Now let's suppose this is for gas phase reaction. For gas phase reaction, fugacity in a solution that can be given by phi I yi p. Okay, so we are just replacing the value of Fi bar. So K is equal to pi of phi I yi p upon p naught whole raised to Vi. So this equation becomes like this: K is equal to pi of phi into pi of yi into pi of p upon p naught whole raised to v. Okay, here there is a vi and here there is a vi. Here the total pressure, so we have to calculate total stoichiometric number. So here I just write total stoichiometric number, where here we are going to take vi, because we are going to multiply each term. So there will be no pi here, there is only p upon p naught. But in a exam told that you have to prove this equation, or prove the equation K is equal to K phi into Ky into Kp. Then this is the same equation as a C. We are just considering K phi is equal to pi into pi I Vi. Similarly, we can consider Ky is equal to pi of yi whole raised to Vi, and we can consider Kp is equal to p upon p naught whole raised to V. Okay, there is no pi here because we are considering all the p, so total pressure is equal to, here becomes the total stoichiometric number. So just replacing this term, so its equation becomes K is equal to K phi into Ky into Kp. So sometime in exam question may be asked like prove that K is equal to K phi into Ky into Kp. So you can prove like this. So this is a equation for the equilibrium constant to composition for real gas. But more generalized form of this equation may be written like K phi into Ky into P upon P naught whole raised to Vi. Now, if I am going to rearrange this equation in term of the equilibrium conversion, then it becomes K upon K phi into P upon P naught whole raised to minus Vi. Okay, so minus, why we are taking minus power, because if I am going to take this side, so it becomes P naught upon P. But if I want to write P upon Pi naught, I can write the Vi bar. Okay, sorry, minus Vi. So this is how this equation becomes, and this equation is known as a relation between equilibrium conversion with equilibrium constant Ky, which is also known as the pi of yi whole raised to Vi. Okay, so don't forget this. Value of Ky is a pi into Yi whole raised to Vi, which is a stoichiometric number. Now, for the ideal condition, K5 becomes 1. Okay, so this equation becomes like this. Ky is equal to K into P upon P naught whole raised to minus Vi. So this is becomes our equation which relates the equilibrium conversion with the equilibrium constant for the ideal solution. Okay, so this is for the ideal system and this is for the real system. So this is for the ideal system. Now let's discuss about the effect of this constant, equilibrium constant on equilibrium conversion. So equation may brighten like this: P upon P naught whole raised to minus V. Okay, so what is effect of equilibrium constant in K? We know that for the uh, exothermic reaction, value of delta H is a negative. Okay, value of delta H is negative. Then exothermic reaction, for exothermic reaction, if we are going to increase the temperature, then equilibrium constant will also increase. So if this value increase, equilibrium conversion is also increased. Sorry, for the exothermic reaction, if we are going to increase the temperature, value of this value of equilibrium constant will be decreased, because in exothermic reaction there is no need of heat. That's why reaction liberate the heat, and reaction liberate the heat, and if we are going to apply the heat to the reaction, then equilibrium conversion will going to decrease, because equilibrium constant will also going to decrease. Okay, so here if equilibrium constant is going to decrease, then again equilibrium conversion is going to decrease. Now the delta H value is positive. Then endothermic reaction, for endothermic reaction, if we are going to increase the temperature, value of K is increased, so that value of conversion will also increase. So this is the effect of equilibrium constant K on Ky. Now let's discuss about the effect of stoichiometric number. Okay, so let's first discuss about the effect of stoichiometric number on this, or effect of pressure on this equilibrium conversion. So effect of pressure is depend on this stoichiometric number. If the value of stoichiometric number is negative, if the value of stoichiometric number is a negative, then this term becomes positive, because minus minus becomes plus. So if I am going to increase the pressure, value of equilibrium conversion will increase. Okay, but value of stoichiometric number is positive, then this becomes negative. So if I am going to increase the pressure, this Ky, value of Ky will be decreased. Okay, so well effect of pressure depend on equilibrium conversion or value of stoichiometric number. So if I am going to increase the pressure, if the reaction or stoichiometric number is a negative, then equilibrium conversion is a increase. But the stoichiometric number is a negative positive, then I am going to increase the pressure, conversion will be decreased. So this is how the effect of pressure on this Ky. But the if value of this stoichiometric number is a 0, so this term becomes 1. So there will be no effect of pressure on equilibrium conversion. So this is the effect of pressure and effect of temperature on equilibrium conversion. We already discussed the effect of temperature and pressure on equilibrium constant. Okay, there is no effect of pressure on equilibrium constant, but here we are going to discuss about the effect of pressure on equilibrium conversion. So this is how the temperature and pressure affect on equilibrium conversion, or how the stoichiometric number is the effect on equilibrium conversion. So there are various other all factors which affect on equilibrium conversion. So one factor which is presence of inert material. uh, how the inert material during the reactions, sometimes we are provide inert material for enhancing the reaction or prohibit the reaction. So for that we are considering the how the inert material affect on uh, some equilibrium conversion. So to understand this, let's consider our equation. K is equal to ky into k phi into P upon P naught whole raised to Vi. Okay, so this is our equation, but we know that Ky is equal to Yi pi of Yi whole raised to Vi. So this is a mole fraction of I component, which defined by the mole fraction of component of particular component I upon total number of component. What is Yi? Yi is a mole fraction. Okay, so we can write that mole fraction is equal to Ni. Sorry, it's not capital N, so it becomes our small n, Ni upon N whole raised to Vi. Okay, so this equation becomes like this if we are going to put the value of mole fraction. So if we are going to use this value, equation becomes Ky is equal to pi of Ni upon N whole raised to V into K phi into P upon P naught whole raised to V. Okay, there is the only V, there is no Vi, because we are considering total pressure. So it becomes V. Now we know that P naught is a 1 bar for the standard state. So this equation becomes Ky is equal to pi of Ni upon N whole raised to V into K phi into P upon P naught whole raised to V. Okay, again here we are just putting the value of this Ky pi of Ni in this equation. So here it becomes K. K is equal to value of Ky we are going to put. So this is our Ky into K phi into P. Okay, so this is only K. So K is equal to pi into Ni upon N whole raised to V into K phi into P upon P naught. But for the ideal solution and standard state, this both becomes 1. So this equation becomes K is equal to pi of Ni upon N whole raised to V into P whole raised to V. So this becomes our equation to find out the how the inert material affects on a particular component. So if we are going to separate this equation, then it becomes like this: N whole raised to V. This is a total number. So here we are going to use Vi. Okay, for I component, but for a total number it becomes V, same as the total pressure, but for Ni we can use Vi. Okay, so it's pi of Vi into PV. So Ni whole raised to Vi is equal to K into N upon P whole raised to V. Okay, so using this equation we can find the inert material, how inert material affect on equilibrium conversion or equilibrium constant. So to find out the how the effect, we can just put the value of inert material in this equation. During the reaction, the mixture with inert material will increase N in equilibrium or in this equation 2. This will be result in increase in conversion if V is positive. So if V is positive, then if we are going to increase total number of composition, if we are going to increase inert material, then this conversion is going to increase. But if stoichiometric number is negative, and if we are going to increase the number of moles, then this conversion going to decrease. So what is effect of inert material? Let again understand effect of inert material. So to understand this, let again write this our equation, pi of Ni whole raised to Vi, which our equilibrium conversion K into total number upon P whole raised to V. Now if we are going to increase inert material, which means we are going to increase the mole. If we are going to increase the mole when the stoichiometric number is a positive, then equilibrium conversion is increased, but the value of stoichiometric number is a negative. Okay, and if we are going to increase the inert, adding inert material in reaction, then equilibrium conversion will going to decrease. So this is how the effect inert material on the particular this reaction. Now if the value of the particular this stoichiometric number is a 0, then there will be no effect of inert material. So if we are going to provide inert material or we are not going to provide inert material, there will be no effect on this equilibrium conversion. Then second factor, which is presence of excess reactant. Sometimes it will be helpful for the reactant will be present in a particular reaction. Increase in number of mole of excess reactant will result in increase in number of mole of product and improve conversion of the limiting reactant at equilibrium. So it is beneficial for excess reactant, which convert our reaction into forward direction. Then next factor, which is the presence of product. Okay, so the if additional product of original reactant stream, then if we are, let's suppose there will be a reactor. Okay, so if we are providing excess reactant, here we are talking about the excess reactant, then this reaction move faster and produce more product. But if we are not going to remove the product and excess product present in this reaction, then it will be decrease the equilibrium conversion. Okay, so if presence of product will be decrease the uh, decrease the equilibrium conversion. So this is how the various factors which affect on equilibrium conversion for homogeneous gas phase reaction. So now let's discuss about relation of equilibrium constant to composition for liquid gas phase reaction. To understand this, let's again consider equilibrium constant is equal to pi of Fi bar upon Fi naught. Okay, so we are just again putting value of Fi bar as we are using in gas phase reaction. In gas phase reaction, Fi bar that represented by phi I YIP, where for the liquid phase is represented by gamma I Xi Fi naught. Okay, so this Fi bar for liquid phase that can be represented by gamma I Xi Fi naught. So if I am going to put the value, it becomes gamma I Xi Fi naught upon Fi naught. So this becomes cancel. So K is equal to pi of gamma I into pi of Xi. Okay. So this is the equation for the relation of equilibrium constant to composition for liquid phase reaction. But if this is a ideal solution, then this activity coefficient is becomes 1. So can say that K is equal to pi of Xi. Okay, so it becomes K is equal to Kx, which is known as a law of mass transfer. And this equation in other term we can write K of gamma into K into X, where K of gamma is equal to pi of gamma Vi. So here there will be a Vi in all brackets, so it becomes Vi. Here also Vi. Okay, so Here also Vi k is equal to pi I xi whole raised to vi. Vi is a stoichiometric number, so k is equal to kx, which is known as a law of mass transfer. So this is all about today's lecture. So in this lecture, discuss about the relation between equilibrium constant to equilibrium conversion. Then discuss for the gas phase reaction. In gas phase reaction, we are using Fi bar is equal to phi I by Ip. Okay, remember this equation. Then we discuss about relation of equilibrium constant to our conversion for the particular component X, or can say that liquid phase reaction. For liquid phase reaction, Fi bar that can be given by gamma I xi Fi naught. Okay. Then discuss about the various factor effect on equilibrium conversion and equilibrium constant. How the equilibrium constant affect on equilibrium conversion, effect of temperature, effect of pressure, effect of inert material, effect of excess reactant, and effect of excess product on equilibrium conversion. So this is all about today's lecture. I am completing my lecture here. Thank you.